Let me introduce Alexandre d'Apremont, who is a directeur de recherche au CNRS at the École Normale Supérieure in Paris. So Alexandre did two PhD, one at the École Polytechnique with Nicole El Karoui, we know because she also gave a colloquium a few years ago. And then the second thesis in Stanford. And the two theses were about optimization.
Yes.
And then he went to Berkeley, and if I am correct, he learned about statistics and machine learning and got involved in the second part of the topic, machine learning. And then he got a position as associate professor in Princeton and went back to Paris a few years ago. So he's a great expert in optimization, especially its application to machine learning. So pleasure to.
Merci beaucoup. Okay, so the last words of French you're going to see today are here, optimization and learning. But I'd be willing to talk about this further in French if you're interested. So today I'm going to talk about convex optimization. And in very simple terms, so don't worry, I'm going to focus a lot and insist a lot on convexity. And hopefully I can try to convince you that convexity is both relatively intuitive and also useful, okay? And I'll talk very, very briefly about two topics directly related to convex optimization, convex approximations of problems that are not convex, and duality. But on the other hand, I'll try to insist a lot on applications, and especially applications in machine learning. And why? Well, to start by a sort of a broad, big picture slide, what happened recently in optimization? Well, it's pretty easy to describe. So why do you hear about big data all the time? Why this sudden buzz about statistics, machine learning, etc.? So one of the ways of explaining that buzz is basically in terms of complexity. So 20 years ago, we had already a pretty large library of algorithms. But on the other hand, the computing power was not there. So we had two options. We could either use relatively naive algorithms on realistic problems, okay? But these problems were too big to do anything sophisticated. Or the other option was to basically use sophisticated methods, but use these methods on somewhat naive problems. So you could only do serious optimization on reasonably large problems, not realistic ones in many fields. So in engineering, things worked fine, etc. But in statistics, you couldn't really do anything sophisticated on realistic data sets. Okay? That was 20 years ago. Now things are completely different. Okay? So today, because we have a lot more computing power, and this is some other field, it's developments in computer science and electrical engineering, thanks to that, now we can at last apply meaningful, sophisticated algorithms we understand well on realistic data sets in statistics, for example. So we knew for a long time that convex optimization was easy, but this had yet to be translated into efficient, workable algorithms that could be applied to large-scale problems. And now, thanks to basically fast laptops like this one, it's finally a reality. So you can apply algorithms that are well understood, for which we have complexity bounds, convergence proofs, etc. And we can apply these methods to realistic problems in statistics. Okay? And that has an impact on the research field itself, and it has an impact actually on many research fields. It means in particular that statisticians have started to care about complexity. So now in statistics, people first study, of course, statistical performance, when do you start to extract signal, etc. But they also care about computational cost. Okay, and that's new. A decade ago or 20 years ago, nobody really bothered about the cost of a procedure versus another, or not that much. Okay, but now people do care about complexity, And they start to study a trade-off that seems to be completely universal in statistics between statistical performance on one side and computational cost on the other. And that's a very active research topic now. Okay, but again, it's completely new, and it's because we can finally understand the complexity of the algorithms we are starting to use in statistics. Okay, and same thing, optimizers have started to care about statistical problems, so a lot of people are working on efficient procedures to solve some of the problems in machine learning I'm going to describe today. Okay, so both these fields have been deeply affected by something that was completely exogenous. Suddenly, we have the computing power to do meaningful numerical work on realistic data sets. Okay, so that's the big picture slide. So a lot of the talk today is going to be about convex problems. I'm heavily biased, of course, so you might disagree on how important this is really, this really is. But still, there's a fundamental message here, and it's probably important to insist on it. Okay, so in 2D, things are very easy to describe. This function on the left is convex. Okay, if I take a chord between 2 points on the graph, it's above the graph of the function, just in case you didn't know. So that's convex, that's fine. And this function here is not convex. Why? Well, I take a chord here, and I'm going to go through the graph. Okay? And so, well, in 2D, this looks kind of boring. Okay? So convex function looks like a very strong restriction on the graph. So how could this possibly be useful or have many applications across many fields? Not clear at all, right? It looks very, very specialized on the left. On the other hand, this is not convex, but again, in dimension 2, this doesn't look that much harder. So minimizing this function, for example, does not look that much harder than minimizing this function on the left, right? And in 2D, it's true. But the point here is that the picture in high dimensions, where interesting problems really live, is completely different, okay? It turns out, and I'm sure your intuition on high-dimensional spaces is much better than mine, but basically it turns out that in high dimensions, convex functions are surprisingly useful and expressive, so many problems turn out to be convex, even though this in 2D looks very restrictive and specialized. So this is much more useful than you would expect. And in high dimensions, this is much harder than you would expect. So as the dimension grows, the number of local minimas and problems in minimizing this function grows exponentially, okay? So the dimension adds up, but the number of local minimums and the number of issues you start getting when you minimize this function multiplies, okay? And so it's really in high-dimensional problems that the dichotomy between convex and non-convex problems starts to show up. So maybe one day I'll be able to show you a nice picture of how things evolve in high dimensions, but for now we're stuck in 2D. And in 2D, it's hard to see why this is the case. And the theory confirms that very strongly. So you can prove, and I'm going to do it very briefly here, that the reasoning is very simple, that all convex problems are easy. And by easy, I mean there is a polynomial time algorithm to solve them, okay? And you can't prove, but it's sort of intuitive too, that most non-convex problems are hard. And we have NP hardness results for many of them, but not all. And every time these proofs are very specialized. So that statement is very important, of course. It means if you're working on an application, you formulate an optimization problem, you work on it a little bit, you show it's convex, you're essentially done. It means that numerically getting a solution is realistic, okay? Then, of course, the complexity matters and not all problems are equally easy, but at least in practice, at least in theory, I would say, and most of the time in practice, you're going to be able to compute a solution efficiently, okay? So all convex problems are easy. What do I mean by convex problem? Well, very easy. A convex problem, at least in this talk, is going to be the problem of minimizing a convex function, subject to a long list of convex inequalities, so the functions fi are convex, and a long list of affine equality constraints, okay? If you're bad with signs, convex optimization is going to be a problem. because if you switch the inequality here, the problem is not convex. Okay? So you want upper bounds on convex functions, and you want to minimize convex functions. So that's a convex problem. Again, this looks relatively specialized. The constraints on convexity seem to be relatively strong, but in fact, this has a surprisingly large number of applications, and I'll try to describe a few today. Okay? In addition to that, even if your problem is not convex, sometimes you can find good convex approximations to give you an approximate answer with, in some cases, approximation guarantees on the quality of the solution. Okay? So suppose you've proved that your problem is convex. Well, typically, as I said, the theory tells you that there will be a polynomial time algorithm to solve it. Okay? But before I go into very quick details on how this method works, the universal method works at least, it's kind of easy to understand why convexity matters so much in terms of complexity. Okay, so take, for example, a differentiable function. So you have a gradient, and you can write an equivalent condition for convexity in these terms. It means that if you compute the gradient at a point in the graph, that gradient will produce an affine lower bound on the graph. Okay? So the tangent here will always be below the graph of the function. Looks trivial enough, right? However, something really fundamental is happening here. Okay? Think about what you're computing. What you're computing here is the value of the function at a point and a gradient. So that's very, very local information, and it's supposed to be cheap. If your function can be computed, typically the gradient can be computed too. So these things are easy to compute and very local. They only depend on the function at the point x. So you get a function value and a gradient, right? Completely local information. However, if you use convexity now, computing this local information allows you to make a global statement about the function, right? Because convexity tells you that this affine lower bound you've computed using the gradient and the function value is a global affine lower bound on the graph of the function, right? In particular, if you're trying to minimize the function, what this information coming from the gradient tells you is that you should not look for the minimizer on the right of this point x, because again, using the gradient and the convexity of this function, you can prove that all the function values on the right of that point are higher. And that means that what you do by computing, again, completely local information is get a global statement on the function telling you I can exclude half of the space of the set of potential solutions. So you cut the space in two by computing a gradient at one point. Okay? From a complexity point of view, that's fundamental. You prune out half of the space by just computing one gradient, right? And that only happens because the function is convex. And it turns out that you can sort of make that argument precise and derive a universal algorithm to exploit convexity and solve convex minimization problems in polynomial time. Okay, and that algorithm is very easy to describe. So here, this is the same graph, but in 2D. Again, you start from a point x0, you compute a gradient, take the affine lower bound going through x0 defined by that gradient. So you have to imagine that the function is sort of growing out. These are the sublevel sets, so it's growing out of the screen, okay? And again, that affine lower bound will tell you all the points in this half space here cannot be minimizers of the function because their value will be higher than the value of the function x0, okay? So again, by computing a gradient at a single point, you exclude an entire half space of points from the set of potential minimizers. So what do you do next? Well, you repeat this operation. So suppose you evaluate the function at several points now, every time computing a gradient. Well, every time you can exclude a half space of points from the set of potential minimizers. And after a while, well, what you've done is you've localized the set of potential points that can be minimizers inside the polytope, right? And the idea of the method now is kind of obvious. What you're going to do is find a new point inside that polytope, compute a gradient, and exclude half of the space from the set of minimizers, hence shrink the size of the polytope, localizing the potential solutions to your minimization problem. Okay? Every time you compute a gradient for a convex function, you cut the space in two, and you localize further the minimizer of that function. Okay? So that's nice, but it's still not clear how to compute the point x. You would like it to be in the center, but that's tricky, so there are all sorts of issues. But the universal algorithm I'm talking about does something a little bit simpler. It localizes the minimizers inside an ellipsoid. Okay? So you start from an ellipsoid where you know the solution lies. You compute a gradient at the center of that ellipsoid, cut away half of the space of potential solutions, and define a new ellipsoid that is the minimum volume ellipsoid containing this half original ellipsoid. Okay, so you start from this one, you compute a gradient at the center, and basically prune out half of the space from the set of candidate solutions, and you localize the solution somewhere here. And now what you do is you compute a new ellipsoid that's the minimum volume ellipsoid containing these points. You're going to add points, of course, here, that cannot be minimizers, but are in your new ellipsoid. But you can show that at each iteration, the volume of the ellipsoid localizing the solution will decrease by a factor that is strictly less than 1. Okay? And that's it. That's all you need. Because you start from an ellipsoid, you compute a gradient. After you've computed the gradient and updated the ellipsoid, the size of the set localizing the solution will shrink by a factor smaller than 1. And that means that by a polynomial number of, if you have a target on the volume you need to localize the solution, the number of iterations you require to get to that target will be polynomial. Okay? We're done. So that's the universal algorithm for solving convex problems. Okay? So iteratively, it looks like this. And typically, it's nice on paper, but if this algorithm actually worked in practice, optimization would not be a field. Okay? We'd have one algorithm solving all problems, and that would be it. Okay? Unfortunately, this dates back from the 60s. The ellipsoid method does not work numerically, or at least is extremely inefficient. So there's a huge library of other methods taking advantage of convexity and some additional smoothness assumptions that solve convex problems much faster. But at least on paper, this algorithm allows you to argue that if you've shown that a problem is convex, then you can get at least one polynomial time algorithm to solve it. Okay? That's really because of convexity. As soon as convexity falls apart, typically your problem will have, you will need an exponential number of operations to get to a global optimum. You can always find a local solution, but it's never clear how good it's going to be and how fast you're going to get there. Okay? So it takes a lot of finger crossing to solve non-convex formulations. Okay, so the most famous example of a convex problem is probably linear programming. And linear programming has an interesting history because the first algorithm for it was developed in the late 40s. Okay, before people knew that computers, well, I mean, the first computers were already there, but there was no linear algebra library. I mean, none of these operations were simple. Okay, but people started to care about the complexity of solving linear programs around the 70s, and the first method to solve it was combinatorial, and the first polynomial time efficient methods to solve linear programs date back from the mid-80s. Okay? And so now you have solvers to solve these linear programs extremely efficiently that you can download off the web for free. Okay? And typically these work even if the matrix A has dimension a couple of millions and is relatively sparse, or A has some structure. Okay, so there's essentially no limit in the size of linear programs you can solve if your problem has a little bit of structure. Okay? What's interesting about most of these convex problems, in addition to the fact that they can be solved efficiently, is that for most of them you can form a dual, and the dual will have the same, so a dual problem, another optimization problem that is directly related to the original one. I'll spare you the details. But the good news about convex optimization problems is that that dual problem typically gives you the same optimum value as the original one. Okay? And it turns out, and I'll try to describe this in detail today in a few examples, that typically the dual problem will give you a lot of meaningful information, non-trivial meaningful information on the solution of the original problem you were trying to solve. So basically with convex problems, you focus on the problem, and for free you get a second problem giving you additional structural information about your solution. And for most solvers, you get both answers for free. So typically, modern solvers will give you the solution to the original problem on the left and also to the dual problem on the right. Okay? I'll show you an example later on. So that's it for the theory. I'm going to switch to algorithms and essentially focus on three striking recent examples. So the list, I could go on and on and on and on, but at some point some of you will want to have lunch. But I'll focus on three developments that are very recent and quite spectacular, both in terms of applications and in terms of what happens on the theoretical side. At least, again, I'm biased, but that's the idea. Okay, the first one is directly coming from machine learning. It's it's something I'm sure you've heard of. It's extremely useful, very flexible, etc. And it dates back from 15 years ago or so, maybe a little bit more. And the basic problem is very easy to describe. You have data, and again, that data typically is in a very high dimensional space. Here it's in 2D, so it's boring, but you have to imagine that this is in a very high dimensional space. So this is, for example, a vector of word frequencies inside a text. Okay, you have a dictionary of words, and for each word in that dictionary, you count the number of times that word appears in a particular piece of text. Okay? That gives you a vector of word frequencies. That vector is a point in space. And typically, a lot of the classification work done on text is done on such representations, so these frequency representations. So you have to imagine that this is an extremely high dimensional space. And now you want to automatically answer questions about the text. Okay? You have an article, and the question could be, is this article about oil? Okay, I don't know. Black points on the left, yes. White points on the right, no. Okay? And now, so you have a couple of articles that are already labeled, so for which you know if they're talking about oil or not. And the idea of classification is you train classifiers on these labeled examples, and you're going to use the classifier to generalize and classify new articles coming for which you don't have a label. So Reuters is doing this. For example, they get a flow of articles all the time. They need to categorize these articles, and they want to do that automatically. Okay? And this could be gene expression data, and you want to classify cancerous cells versus healthy cells. This could be in vision. It shows up everywhere. Okay? So one way to do it, at least the most basic way of doing it, suppose you have these two clouds of points. The idea is how can you find a classifier, a linear classifier that splits the space in two and perfectly classifies these two clouds of points. Okay, that's linear classification. And linear classification is easy because, well, if your data points are the points xj in Rn, for n pretty big, and you have labels yj plus 1 minus 1, okay, defining the two classes. The problem of finding a linear classifier that perfectly classifies your data can be written very simply as a linear programming feasibility problem. Okay? So you want the scalar product between your classification vector and your data points in one class to be greater than 1, and you want the scalar product to be smaller than 1 for the other class. Okay? If you it's minus 1 and 1 here, but it doesn't matter. No, here it's plus, greater than 1 and smaller than minus 1 because everything is homogeneous. So you fix a value arbitrarily. There are variations on this depending on what you really want. Okay? But so that's basically a linear programming feasibility problem. Yeah. So it's easy to solve. Okay, so finding a linear classifier that splits your data into groups is easy. Okay, but it's not particularly spectacular. It turns out that, and that's the first sort of amazing trick about classification, linear classification and nonlinear classifications are not that different. Okay? Because the nonlinearity is in your data, not in the problem you're trying to solve. Okay, so suppose I want to do nonlinear classification and use a polynomial to classify my points. Well, I can always add, so this is the square of the vector j, so it's coefficient y square. I can always add monomials to my vector, my data vector, constructed from the data itself, and find a larger vector of coefficients for this polynomial now that I'm going to use to do classification. But in the end, the problem I'm solving only applies to the coefficients, and the classification problem is still linear in the coefficients of the classifier. So even now, though the data is now highly nonlinear and the classifier I'm going to use is highly nonlinear, the problem I'm solving is still linear and convex, easy to solve. Higher dimensional, but still convex. Okay, so that's the first striking news, and I'm going to come back to this about classification, is that nonlinear classification is not that much harder than linear classification. So suppose my two clouds of points are like this, and I want to separate them classify them using an ellipsoid. Finding that ellipsoid is really easy, and it amounts to solving an LP. Okay? All the nonlinearities in the data, not in the problem you're trying to solve. So this problem is basically as easy as the original naive linear classification problem I've detailed. Okay, same thing with fourth degree polynomial, there's essentially no limit. Okay? So that's already a pretty striking point, because of course linear classification is too restrictive in many cases, and you want to use non-trivial classifiers to classify your data. Okay? But you can do more than that. So suppose that your data sets are not separable. It's very easy to include slack in the classification constraints and minimize the error. It's linear, it's convex, it's easy, etc. So minimizing the slack is again a linear program, no big deal. Suppose also that on the other hand, you have many classifiers, linear classifiers that perfectly separate your data. You want to pick one that's well aligned with the geometry of your data set. And one way to do that is to maximize the margin between the classifier and the clouds of points. Again, that's a convex problem. It's easy. Okay? Typically, what you do is optimize a mix of both. Your data set cannot be perfectly separated, so you minimize the classifier error on one side, but you don't want to overfit your data, and so you regularize your classifier at the same time. Okay? If you fit your data too much, typically you're not going to learn much about new points because your classifier becomes too specialized and exotic. Okay? So what you do is you penalize your classifier to make it as simple as possible, and that tends to improve generalization performance. But that's for another day. Okay? So in the end, the problem you're trying to solve looks like this. That's a fairly generic support vector machine classification problem to do maximum margin classification. So you're minimizing a regularizing term on your classifier, that's here, a term measuring the classification error on your training set, and you have a long list of classification constraints. Okay? That's a convex problem. It can be solved extremely efficiently. It's useful, so people have developed very fast algorithms to solve this problem in practice, but that's for later. Right now, we have a convex problem, and we want to know if its dual is interesting. Okay, I told you that every convex problem has a dual, and that typically this dual gives you information about the original problem. Let's see what happens with classification. Okay, so that's support vector machine classification. The size of this problem depends on the size of X, the original space where you're doing the classification, and the number of training points you're getting in solving the classification problem. Okay? Well, if you want, forming the dual is always a little bit the same procedure. You start to replace you transform the constraint problem into a non-constraint problem that's here. So you add a penalty for the constraints in the original problem. So you have this function here. And what happens, and I'm going to spare you the details here, is that if you minimize this Lagrangian function, the unconstrained version of the problem I've just detailed, in the original variable, you find a lower bound on the optimum of the original problem you were looking at, okay? So every time you minimize this in X, you get a lower bound on the original problem. And now, of course, this is optimization. You're interested in the best lower bound you can possibly find. And that's how you form the dual problem, okay? And the dual problem turns out to be another convex optimization problem. And you can show that in most cases, the optimum value of this problem is going to be equal to the optimal value of the original problem. Okay? Here, in addition to that, you can see that you can reconstruct a solution from a classifier W solving this problem from the solution of this optimization problem here. So that's the dual problem. Okay? It's a problem that you've derived from the original one, but right now it doesn't really have an interpretation. Okay? But if you study and reformat this problem a little bit carefully, it turns out that it looks like this. Okay, so you're optimizing in alpha, a quadratic function, but there are two important facts about this optimization problem. The one really striking aspect of this problem is its dimension. Okay? Remember, we're doing classification in a space of dimension n, could be arbitrarily large. And the first thing you notice about the dual problem here is that n does not appear in its formulation. Okay? The size of the dual problem grows with m, the number of training points, but not with the dimension of the space in which you're doing classification. In particular, it has a strange statement. Once you've computed that X transpose X matrix here, okay, the complexity of solving the classification problem is independent of the dimension of the space in which you're doing classification, right? This is as close to a free lunch as you're going to get in optimization. Okay, you're doing classification in infinite dimensional spaces, no problem. The size of your problem is still growing only with the number of training samples you're getting. Okay? And the second statement that's important is that actually all the information about the geometry of your data set that you care about is contained in this matrix X transpose X. That's a positive semi-definite matrix, and in classification it's called a kernel. Okay? So all you need to describe your data and do classification is a good kernel, a positive semi-definite matrix that describes, roughly speaking, the scalar product between your data vectors in the space in which you're doing classification. Okay? And it turns out that people have discovered very quickly that you don't even need to form the matrix X to do classification. If you know how to produce a kernel matrix directly, you save a lot of time because you never go into the high dimensional space where everything is expensive. You form the kernel matrix directly, and that the size of that matrix grows only with the size of your training set. And again, it looks a little bit innocent here, but the fact that you don't really pay a price for doing classification in high dimensional spaces means that the method can be applied to pretty much anything. And so there's an entire industry that was developed around the problem of manufacturing kernels that well represent the structure of somewhat complex data. Data like voice, for example, or data like gene sequence alignment, where now you have these you're computing edit distances between two sequences of gene, etc. So the classification space is very abstract and high dimensional, but in practice, you don't care because all you need in the end to do classification is that kernel matrix, and people know now how to produce kernel matrices from gene sequences by doing edits and so on. Okay, so there's this huge industry of taking data sets that are highly complex, heterogeneous, and so on, like voice, a mix of voice, images, text, etc., and compiling kernels out of these data sets to do classification without paying the price that you should be paying for doing classification in very high dimensional space. Okay? It's a little bit of a miracle. So again, this works on images, it works on text, where you look at frequencies and you compile them into a vector and then get a kernel. There are many ways to do this, but this is a huge industry, and it works. So on text, for example, doing simple task of text categorization, the performance of these algorithms matches the performance of humans. Okay? And it's true in many fields. The one field that's still very hard and out of reach is vision. We are much better at vision than machines, and it's going to be like that for a while. Okay, but it seems that our brain, a lot of our brain is, most of our brain is focused on processing visual information, and we're quite good compared to machines. Okay, but on simple tasks like text classification or classifying healthy versus diseased cells and so on, the performance of machine is almost better sometimes than the performance of humans. Okay, so for text categorization, you get precision rates of closer to 95 or 98%. Very, very few errors. And humans don't do much better than that, okay? Because a lot of these questions are typically ambiguous, plus there is noise. Okay, so that's one important success story. Okay, again, magic here is that the dimension of the space in which you're working completely vanishes from the optimization problem. Second success story, compressed sensing. So compressed sensing, again, emerged, say, 10 years ago, but it's tricks that people have known for years. It's just that now we know how to justify them. Okay, and the story is very easy to describe. Again, here, this is, so good applied mathematics is never completely distinguishable from magic, and this is magic. Okay, so you're trying to solve a linear system that's significantly underdetermined, right? So you have a few equations and a lot of unknowns. So the space in which you're working is, again, very large, and you have much fewer equations. So you know that this is desperate, okay? Or at least you're going to get an entire space of solutions. But here you have one additional piece of information. You know that the solution you're looking for is sparse. In other words, that only a few of its coefficients are non-zero. And it turns out that under certain configurations, of course, this extra information is enough to completely specify the solution. So a lot of attention now is focused on solving these linear systems, underdetermined linear systems, with this additional sparsity assumption. Okay? So the first question is, can you show that there exists a unique solution with minimum cardinality? First thing. Second, can you compute it? Okay? It's very nice to show existence and the fact that the problem is well posed, etc. But if you can never compute the solution from a practical point of view, it's not terribly useful. Okay? But here we're lucky because the answer is yes in both cases. Okay, so the idea is you have this underdetermined linear system and you want to find its sparsest solution, the solution with the minimum number of non-zero coefficients. Okay? So it's easy enough to describe in abstract terms, but why do we care about sparsity here? Well, it turns out that, well, there are direct applications of this in signal processing. For example, you know that a lot of natural signals have a sparse representation in a certain basis. Okay? And so typically, if the signal you're trying to construct has this sparse wavelet representation, for example, you want to penalize to recover a signal. Even though you're missing a lot of information about your signal, you want to penalize the solution so that it has this feature of being sparse in a certain basis you know. Okay? So that's the signal processing point of view. Same thing in coding theory. You're observing, you're getting a signal, but that signal is corrupted by a few errors. Up to what number of errors can you still recover the signal exactly? Okay? Or in statistics, you're doing regression, but you know only a certain number of variables, a few variables really count in describing your regression outcome. Okay? Can you isolate these variables, the ones you care about, from the noise? Okay? So the reason why sparsity shows up so often is that sparse signals are very, very common in nature. Okay? So word frequencies in natural language follow a power law. And here, basically, sparsity in all these problems is understood as a proxy for following a power law. Okay? It's sort of a rough approximation. A vector that is sparse is sort of a rough approximation of a vector whose coefficients follow a power law. Okay? And power laws are absolutely everywhere. Word frequencies in natural language, ranking coefficients on the web, signal processing, you have 1/f signals. In social networks, the node degree follow the power law, earthquakes, I don't know why, river systems, etc. So these power laws are everywhere. So this is, for example, frequency versus word, number of words in Wikipedia. Okay, so you have one word that shows up 10 to the power 7 times, and then you have about 100 words who show up 100,000 times, and so on. Okay, but in semilog, in log-log scale, you get almost a perfect line. That's Wikipedia, all of Wikipedia. Okay, it's amazing to see how smooth these plots are, right? Same thing with earthquakes. Okay, there's a little bit of noise at both ends, but earthquake, magnitude versus frequency in log-log scale, perfectly linear, very smooth. Okay, page rank. You compute the page rank of web pages. Okay, same thing, log-log scale, linear, very, very smooth. Okay, and it shows up everywhere. Protein interactions, the web, so the structure of the graph, citation in science, collaborations in math, the internet, so the structure of the network itself. All of these have power law distributions. Okay, and the one example that matters a lot too is images. I don't have an illustration right now, but images, typically if you do their decomposition in some well-chosen wavelet basis, will have a very sparse representation. So sparse signals are everywhere in nature. And so this problem of finding the sparsest solution to a regression problem, for example, is deeply meaningful because sparsity is a highly meaningful structural assumption when you're solving statistical or imaging problems, for example. Okay, so explicitly the problem you're trying to solve is this one, minimizing the cardinality of a vector x that solves an underdetermined system of equations. And at first, you think, well, this is bad news. Minimizing the number of non-zero coefficients is counting. Counting is typically non-convex and really hard. And you can show that in the general case, this problem is NP-complete. So there's no hope of finding a universal algorithm that will always give you a solution in polynomial time. Okay? But for a while, people have studied a natural convex approximation to that problem where you minimize the L1 norm of the vector x, so the sum of the absolute values of the coefficients, instead of the number of non-zero coefficients. And for the last 40 years, people noticed that this simple trick works very, very well. But we didn't know how to show it. Okay, and this is easy to see on a small numerical experiment. Okay? So what do we do here? You fix the matrix A. And we're going to try many experiments. So we generate random sparse signals E. So E has random coefficients, but only a few of them are non-zero. Okay? And we plot in this graph here the probability of recovering E by solving this problem, the L1 minimization problem. It's a heuristic to find the sparsest solution to the linear system. Okay? And every time the solution of that problem matches E, the original signal, you record success. Every time it doesn't, you record failure. Okay? And the good news is that this is a convex problem. In addition to that, you can write it as a linear program, so it's very easy to solve. You can download the solver of the web to get an answer really quickly, even for very large-scale examples. Okay? And what you notice is that there's this very spectacular phase transition here in the recovery performance. Meaning that if your signal E is sparse enough, so has few enough non-zero coefficients, then the solution of that problem will always exactly reconstruct your original signal E. Even though you're working in a space that's much larger than the number of samples you're getting, so you have 100 samples in a space of dimension 1 million, okay? Provided the size of your signal is relatively low, so your signal only has 10, 20, or 30 non-zero coefficients, you're going to be able to recover it exactly, even though your observations make the problem deeply underdetermined, okay? So this extra assumption that your signal is sparse completely nails down the solution X, and in addition to that, you can show that you can recover X by solving a problem that's tractable. It's a linear program, it's convex, okay? So you have this spectacular phase transition, and in addition to that, we know how to quantify where this phase transition occurs now for certain type of matrices A, okay? So we know that for random matrices A, for example, the number of experiments required to exactly recover a signal of size k is roughly speaking proportional to k. And that's very striking because you cannot hope to do better than that, up to a few coefficients and logs, etc. Okay? To reconstruct a signal with k non-zero coefficients, you need at least order k observations. Okay? There's no escape. What the theory tells you here is that that's enough. That's all you need. Okay? And furthermore, the procedure to reconstruct your signal, even if in essence the problem is deeply combinatorial, the procedure to reconstruct your signal is polynomial. Okay? Very spectacular. People knew this thing worked as a hack, but now we have theory to prove that the hack is actually working with very high probability for random matrices, for example. Okay? So that has a lot of applications in signal processing, magnetic resonance imaging, and so on. Okay, so that was the second sort of second miracle, minor miracle for today. Okay, last one is semi-definite programming. Okay, so this you should all be familiar with. That's a linear program. You're minimizing a linear objective. I've showed a few already. You have linear constraints and a constraint on the positivity of the coefficients of the solution. Okay? So we have an algorithm for solving this called the simplex, dates back from the 40s. It's potentially exponential. We also have polynomial time, efficient algorithms to solve this problem in practice. Linear programming has tons of applications everywhere, etc. So this is a well-understood problem. Okay? Semi-definite program looks very similar. In a semi-definite program, your variable is now a symmetric matrix, X. But on the other hand, the objective is still linear in X. Trace of Cx is the scalar product between C and X. It's linear. Okay, and you have a long list of affine constraints. Trace of AI X equal Bi. So it looks, again, affine. This looks very much like a linear program. The main difference, though, is that the constraint on your matrix X is a bit different. What you want is that the matrix X solving this problem is positive semi-definite. All its eigenvalues should be positive. Okay? So the cone of positive semi-definite matrices is convex. So this is a convex problem. Okay? So in theory, at least, you should be able to find a polynomial time algorithm to solve it. But for a very long time, people thought that these problems were out of reach numerically because they were highly nonlinear. And the original way of thinking about complexity in optimization was to say linear problems are easy, nonlinear problems are hard, and the higher the nonlinearity, the harder the problem gets. Okay? That's completely false. Completely. Okay? So nonlinearity has absolutely nothing to do with complexity, and semi-definite programming is one striking example of that fact. Okay? This is as nonlinear as it's going to get. You have inequality constraints on eigenvalues. Okay? So it's the constraint here is non-differentiable, nonlinear, it's non-whatever you want. Okay? However, what people discovered in the mid-90s is that there was a very natural extension of the theory used to produce efficient solvers for linear programs that allowed these solvers to be applied directly to semi-definite program with very similar complexity bounds. And that the analysis of these problems, both from a theoretical and from a computational point of view, was very similar to the analysis of linear programs. And using these results, people started producing very efficient solvers to solve these problems in relatively high dimension. Of course, the number of variables here grows as the square of the matrix dimension, so you cannot expect things to be tractable in dimension 10 million, okay, like they are for linear programs. But on the other hand, the solvers look very similar, and their performance and reliability is now very similar to the performance and reliability you get from linear programming solvers. Okay, and this is due to a theory called the self-concordant analysis of Newton's method. I'll spare you the details, but if you're curious, this is a very, very clean, what you get from these results is very, very clean, almost constant and dimension-free bounds on the complexity of Newton's method for solving problems of this type. Okay, very, very spectacular. Okay, and so basically what happened with semi-definite programming is very similar to what happened with linear programming in the late 40s, early 50s, 60s, and so on. So when linear programming was first studied in the late 40s, it was a toy problem. There were no computers, no nothing. They had to be solved by hand. So the first large-scale linear programs had 9 variables and 15 constraints, and they were solved by a bunch of soldiers stuck in a room for an afternoon or so. Okay? So, of course, at first, this was a sort of an oddity, a scientific curiosity, but linear programming didn't have a lot of applications. But as numerical packages were developed and computers became cheaper in the 60s, people started finding many applications for linear programming all over the place. And people got efficient solvers, etc. So linear programming now is almost a technology. Everybody uses it. It's fast, efficient, reliable. It's industrial scale, right? And it turns out that more or less the same thing is happening with semi-definite programming. So at first, it was a scientific oddity that you could solve these problems efficiently. But okay, so positive semi-definite matrices are covariance matrices, so there is a number of natural applications. But it turns out that because people started hearing that these problems could be solved efficiently, they started trying to recognize them in many applications. And it turns out that semi-definite programming has a pretty significant expressive power. So you find semi-definite programs in places where you don't expect them. So testing the positivity of a polynomial, for example, on the real 9, is equivalent to writing a linear semi-definite program. Okay, things that are somewhat unexpected. Okay, and so now there's a sort of growing library of problems that are formulated as semi-definite programs and hence can be solved efficiently. Okay, and so semi-definite programming is sort of slowly following the path of linear programming. So I want to focus on one today, last story of the day, and it's coming from Netflix. So Netflix is available all over the world except in France, and it's a very nice video-on-demand site, okay? And it has about, I mean, the last time I compiled these statistics, it had about 25 million users and 60,000 films. I think by now it's probably 80,000 and 50 million. So it's video on demand. I think I don't have to explain. But what Netflix cared about a lot is they want to keep people interested, okay? And they also have a slightly odd problem. For many video-on-demand websites, the catalog of film is relatively small, okay? And so the idea is to keep people interested in a small set of films, so you push them heavily and that's it. Netflix has a slightly different problem. They have to manage abundance, okay? They have lots of film, and to keep you interested, they want you to discover films you like, but are deeply buried inside their catalog, okay? So what they really need is a good recommendation engine, okay? And so what they ask of you every time you watch a film is to rate it. So you put a rating 1 to 5 stars, or like it, didn't like it, if you want to make it simple, okay, +1, -1. And the idea is to go beyond the sort of traditional rating framework where you just publish the average rating people gave to a particular film, okay? The idea here is to produce personalized ratings. So beyond the average rating, what you want to say is people who have similar taste to yours have given that particular grade to that particular movie. So you observe a matrix of ratings. So here, of course, it's very sparse because not everyone watches every movie, especially when there are 60,000 of them, well, even in academia. And, but you still have a lot of information about many users and many movies, okay? And from that single matrix of ratings, you want to reconstruct two things now. you want to get some information about movies and sort of classify movies, but you also want to learn some information about the users and classify user, cluster them, okay? Implicitly at least, okay? And again, the point is to make personalized recommendations. And so it looks like this in practice, okay? So they want to look at your the catalog of movies you've watched and make recommendations. So here it's not so bad. Memento is nice. I don't know the other. This one is classic, in any case. So the problem was studied in a very, very simple framework at first, and this turns out to be surprisingly efficient. So what they assume, what people assume in this, the problem is called collaborative filtering. So in collaborative filtering, people typically assume a linear model. And what I mean by that is that they say that the rating is the product of a scalar, is computed as the scalar product between a vector U representing user features, user characteristics, and a vector V representing movie features. You take these two vectors, one representing the user, one representing the movie, take the scalar product, and you get a prediction on the rating for that particular movie, for that particular user. Okay? So if you look at things this way, collaborative filtering, or the problem of learning these vectors U and V, can be seen as a matrix factorization problem. You are given M, and you want to compute U and V such that M is well approximated by U transpose V. It doesn't take very long to realize that this problem is somewhat ill-posed, okay? Because there are countless ways of representing a matrix as a product of two other matrices. Just pick V equal to the identity, for example, and U is quite easy to find, okay? So you need to be a little bit more specific about the kind of matrix you're looking for. And here, again, there's a natural sparsity assumption at play. Your additional assumption or requirement on the structure of the model is that it's going to be simple. So that there's a simple vector representing movie characteristics and a simple vector representing user features. What do I mean by simple here? Well, U is small, has, let's say, a few coefficients. V is small too, hence U transpose V. Both U and V are low rank. And so what you want is here a low rank approximation of the matrix M. Okay? And that sounds completely natural. So in practice, the problem you want to find, at least in a binary rating format, is the problem of minimizing the rank of matrix X, approximating the rating matrix M that has minimum rank and doesn't make too many errors in the prediction for coefficients for which you know the true rating. So suppose here you're predicting 1 and M is 1, this thing is going to be small. Suppose you're predicting -1 and M is 1, this thing is going to be large. Okay, so that's an error term. It means that you're fitting very well the data, and this means that you're fitting well the data with a matrix that is low rank. Okay? Again, this problem is combinatorial. So in theory, there's no hope to find an efficient solution, an efficient algorithm for solving it. In practice, again, based on this set of sparsity results for solving sparse linear systems, finding sparse solutions to linear systems, extensions of these results have been derived for matrix problem written over matrices. And it turns out that people have shown that you can approximate this problem, combinatorial problem, by a nice convex optimization problem here. Okay? And you're replacing the rank of the matrix X by its nuclear norm, which is essentially the L1 norm of its spectrum. Okay? So this is a direct extension of the sparsity results I've just detailed. That problem can be solved efficiently. It's a convex semi-definite program in the matrix X. Okay? And so we have efficient solvers to solve these things. Okay? And so it's funny because the Netflix challenge got very popular because Netflix offered $1 million to anyone who could improve the performance of its rating system by more than 10%. And there was a progress prize for the person who made 1% progress as fast as possible. And it took 2 weeks to beat the 1% mark and 3 years to reach 10%, which was very well calibrated in some sense. But for $1 million, they pretty much hijacked the entire US postdoc community in machine learning for 1 year. So they got a pretty good deal on the consulting. Okay? And so the story could end here, okay? Collaborative filtering is an important enough problem, but it turns out that matrix completion has surprising applications beyond simply making recommendations about movies or products. Okay, so I'll finish with this very simple example. So diffraction imaging of molecules. So you cannot look at molecules because they're too small, and you have to use diffraction patterns to infer their structure. And we don't know yet how to do that. So for large molecules, there are several techniques to give you their structure, but in many cases, we don't know what they look like. And if you don't know what they look like, you don't know what they do, okay? Because function follows from form. And so there's a lot of work now on trying to get images of molecules indirectly. And one of the ways to try to do that is to use diffraction imaging, phase reconstruction. So the way it works is that you have a large X-ray source. It's an X-ray laser. You project coherent light on the molecule that's here. And that then, in turn, projects a diffraction pattern on a sensor somewhere here. Okay? The sensor loses the phase of the signal, but records the magnitude. If you had the phase, then you would simply invert the two. Here is the 2D Fourier transform of the molecular density. If you had the phase, you could simply invert the Fourier transform and recover the density. You're losing the phase. And the problem in imaging, in diffraction imaging, is to reconstruct the phase from your observations to reconstruct the density. Okay, so you have to solve an optimization problem over the phases of each of these observations here, each pixel. Okay? The problem, in essence, can be written in this format. So you're trying to solve a linear system, except that you only observe the square of the coefficients of the scalar products, not the scalar products themselves. So this would be a nice linear system, except that you're only observing basically the absolute value of A transpose X. And you have to reconstruct the signs or the phases to be able to reconstruct the solution. And it turns out that based on all this activity in collaborative filtering and in matrix completion and so on, people realized that you could write these constraints in matrix format, and that the phase recovery problem that you use in diffraction imaging could be written equivalently as a completion problem on a semi-definite matrix. So what's the problem here? You have a matrix X that satisfies a certain number of observations, like the ratings matrix, for example. You know it's positive semi-definite, and you're trying to find a minimum rank solution matching your observations. So it turns out people realized very recently that the diffraction imaging problem can be directly written in terms of collaborative filtering or matrix completion problem. And that all the results we had for making movie recommendations could be directly applied to the problem of reconstructing molecular densities in molecular imaging experiments, which is a nice surprise. You think you're working on movies, but in the end, you're making, you're reconstructing images in diffraction imaging experiments. Okay? So that's it. I'm done.
Your results concerning the approximation of sparse solutions or minimizing the rank of matrix and so on are reminiscent of a problem of which I don't know a good solution, which is compute the Nash equilibrium of, say, bimatrix nonlinear game problem. Are there any attempts at Nash equilibria?
I think there are, but I'm not. I don't have the results in mind. So I think there are. I don't know exactly in which settings.
And where should I like? where should I look for to find that?
Google Scholar.
Okay.
That's you can send me an email, but I don't have precise references in mind. So there are algorithms specialized to matrix games that are very efficient, but they only work in a certain setting. And for Nash equilibrias, I don't really know.
The zero-sum, two-player zero-sum matrix game has long been known to be equivalent to a linear program.
Yes.
It's due to Gale.
Yeah.
And this dates back to the late 40s.
Yeah, but because of its structure, you can actually solve it if you care about these things in very, very large dimensional, because it has a lot of structure, so you can hope to solve very large scale problems in this case.
I've done it.
Well.
Or my students students have done it. I don't program very well.
But for
my
Nash,
students
I don't
have
know.
done it.
For Nash, I don't really know.
Okay.
Thank you for your nice talk. You said that these techniques don't really fit to vision problems, vision issues.
Oh, they do. So there's a lot of work now on vision in Paris in particular, at INRIA and so on. It's just that the performance that these methods and other methods like neural networks and so on are reaching on vision problems is still pretty pathetic compared to the performance of humans on the same problems. We're very good at parsing images, recognizing objects, distinguishing foreground from background, etc., naming entities in an image. And these are problems for which there's a lot of work now in machine learning, but the performance of the algorithms that are being derived is still vastly inferior to the performance of humans. And that's not the case, for example, in simple text classification problems, where these methods produce performance or recognizing digits on envelopes, okay, single digits, zip codes, and so on envelopes. We are reaching performance that's pretty close to what humans do. Text classification, categorizing text, it's the errors these algorithms are making is completely comparable to the errors a human would be making on the same problem. Okay, so that's true in many fields. There are fields where these algorithms detect classification patterns that humans cannot detect, but in vision, empirical performance is still way inferior to what humans can achieve. Vision is much harder.
But is it a status, or is it, do you have an intuition why these tools are not as efficient? Is it because vision is something else?
Vision it's a lot. First, the volume of data is much higher. Okay, so the volume of data you're getting through your eyes is massive. So there's a problem of size. There's also invariance issues. So we are very good at pruning out invariances in visual observations, so changes in light, configuration, rotations, etc. For algorithms, this is still a pretty big open problem. Finding representations of images that are sort of invariant with all the natural invariances we naturally prune out is still an open problem. So there are all sorts of things we do completely naturally that we cannot reproduce numerically yet. And other than that, only fools claim they know the future. So I'm not going to make predictions about future performance, right?
So, some of the algorithms you mentioned are very efficient because they use the convexity, like the cutting plane or the level method of Nesterov. But on the other hand, the ellipsoid algorithm is not very efficient, but it doesn't use convexity, it uses quasi-convexity.
Right.
So do you think this could be the explanation why it is less performant? And do you know efficient algorithms that just use quasi-convexity?
No, I don't. But on the other hand, there are sort of variations on the argument behind the ellipsoid method that turn out to be very efficient in certain settings. So one of them is the analytic center cutting plane method, where instead of localizing your set using an ellipsoid, you localize it using a polytope, and you then use the analytic center of that polytope to compute your new query. And the convergence of these methods is typically linear, so extremely fast. And so you get to good solutions very quickly with a minimum number of assumptions. And these methods are typically a good choice when evaluating a single gradient is extremely expensive, and you want to evaluate as few gradients as possible. So it's the same setting as the ellipsoid method, but it's implemented in a more efficient way. So there are variations, efficient variations on the ellipsoid method, but it's a bit more specialized.
For nowadays, issue that or problems that I'm working on vision and we have many problems. But do you think it's more a problems of algorithm to compute the mathematics how we express our problems, or it's more a problem of bias or outliers? you didn't say anything about how robust are those methods according to our
the reason I didn't go into detail into vision is that I'm not at all an expert. So
I mean, no, just take the example of vision, but of course it's universal. When you take a problem, you have the issue how to solve it, but you have to know also how good is how you write your problems.
Yeah, absolutely. So for now, we don't even have. It's not a numerical complexity question. So I think I understand your question. So it's not that we have the right problem and we don't know how to solve it. It's that we're not even sure we have the right problem, right? Mm-hmm. So in vision, that's trickier. The classification problem I mentioned seems to be enough in many fields because we have the good data representation, and it then just becomes a numerical issue, but it doesn't seem to work and have all the invariance properties we need in vision problems. So the underlying theory, in addition to complexity issues related to the size of the data, etc., there are clear modeling issues that are unresolved on the vision front. But I'm not at all an expert, so you should talk to Jean Ponce.
You mentioned several success stories, and I would like to know whether you can foresee the new one, or at least if...
Or you want to hear about the failures?
No,
new
the
one,
next success stories. What are the main open problems and what progress can be made?
So there's a lot of work now clearly on streaming data. So because the data sets are getting larger and the data is delivered to you in a slightly different format, and you cannot solve problems in just batch mode where you look at all the data at once and compute the optimum solution by solving a single algorithm. Typically, you get the data by piece, and every time you get a new piece of data, you need to update your solution and improve the current point. So we understand very well the complexity of solving problems in batch mode, but we don't understand that well the complexity of solving problems when your data is not accessible all at once, very easily, all in memory, and so on. Okay, so clearly that's completely open. Distributed optimization is completely open. Despite years of work on parallelization and so on, most of the algorithms I've mentioned are sequential in nature. And the complexity bounds are computed for sequential operations, and you can distribute the linear algebra behind them and so on. So there's a lot of work on that. There are simple problems that can be solved in a distributed way, but there's no magic. So it's always kind of an engineering rational approach. There's no magical breakthrough in distributed optimization yet, as far as I know. And then I think the last point is clearly when you work at the interface between optimization and statistics, there's an obvious trade-off between statistical efficiency of the procedure of the estimator you're computing and the cost of computing it. And you push on one side and things blow up on the other, everywhere. But all we have now is observations. So there's a trade-off curve between statistical performance and computational complexity. And all we have is a couple of points on that curve, and we don't know where it comes from. So we don't know why better estimators are more expensive. There's no explanation so far. A couple of observations, certain bounds are starting to emerge, but this is clearly a very active topic in statistics and optimization. We want to understand what's the connection between complexity on one side and statistical performance on the other. And I'm sure things will emerge there that would be interesting. So the idea in particular would be to rewrite. Right now we analyze the complexity of an optimization problem first in terms of convexity, but also in terms of smoothness, etc. And it's clear that these descriptors of a problem characteristics are not appropriate for statistics. So difficult or easy statistical problems are classified according to something else, and we need to make the connection between that something else and the description of the complexity of algorithm to solve them, and completely open.